Tonight, we're going to explore one of the most profound questions in human history. Not the question you might expect about whether human beings will ever set foot on Mars, but a deeper one about whether the first people who do will ever come home again. Because the journey to Mars is unlike anything our species has ever attempted. The moon sits 238,900 miles away. Apollo astronauts crossed that distance in 3 days. Mars, at its closest, lies 34 million miles from Earth. At its farthest, nearly 250 million. Launch windows open only once every 26 months. The transit alone takes 6 to 9 months in each direction. A radio signal that reaches the moon in a second and a half can take more than 40 minutes to cross the Gulf to Mars. And once you understand the true weight of those numbers, a quieter truth begins to surface. The first humans to walk on Mars may never be coming back. Not because something went wrong, but because staying was the plan all along. By the end of tonight, you're going to understand why a return journey from Mars sits at the edge of what physics and economics allow, why the people who go will go anyway, and what it means to become a multi-planet species. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about what every explorer who ever left home had in common. Magellan's crew set sail from Spain in 1519. 3 years later, in 1522, the survivors returned. Edmund Hillary reached the summit of Everest and walked back down. The Apollo astronauts touched the moon and splashed into the Pacific. The pattern held across every expedition in human history. You go out, you discover, you come back to tell the story. That structure was so constant, so assumed, that it barely registered as a choice. Return was simply what exploration meant. Mars breaks that pattern, not bends it, breaks it. To understand why, you need to understand distance, real distance. Not the kind measured in miles on a map, but the kind that reshapes what is physically possible. The moon sits roughly 239,000 miles from Earth. That is far by any everyday measure, but in space terms it is close enough to almost feel like a neighbor. The Apollo missions crossed that gap in about 3 days. A full lunar mission, from launch to splashdown, lasted 8 to 12 days. And communication between Earth and the moon took about 1.5 seconds each way. 1.5 seconds. Mission controllers in Houston could talk to astronauts on the lunar surface and hear a response almost immediately. The moon was distant, but it was reachable, manageable, and above all, connected. From the lunar surface, astronauts could look back and see Earth as a blue and white marble suspended in the dark. Small enough to cover with a thumb, close enough to feel like home was still visible. Mars is not that. At its closest approach, when both planets align favorably in their orbits around the Sun, Mars sits about 34 million miles from Earth. That is roughly 140 times the distance to the Moon. At its farthest, when Earth and Mars are on opposite sides of the Sun, that gap stretches to nearly 250 million miles. And it never stays fixed. Both planets are moving continuously, tracing their own separate paths. So the distance shifts every single day. That variability creates another problem. You cannot simply decide to go to Mars whenever you are ready. The geometry of the two planets' orbits only lines up favorably for a launch window once every 26 months. Miss that window, and the next one is more than 2 years away. There is no other option. No shortcut. The planets do not negotiate. When a spacecraft does launch during one of those windows, the journey to Mars takes 6 to 9 months, depending on the trajectory chosen. 6 to 9 months of transit. Alone, in deep space, with nothing between the crew and the void except the walls of the spacecraft. The moon mission was a long weekend. The Mars transit is closer to a full pregnancy in duration, with no option to turn back once the trajectory is locked. But the distance does something else. Something that changes the nature of the mission in a more fundamental way than transit time alone. It kills the phone call. A radio signal traveling at the speed of light, takes about 1.5 seconds to reach the moon. That same signal, sent toward Mars at its closest approach, takes roughly 3 minutes to arrive. The reply takes another 3 minutes to come back. 6 minutes for a single exchange. And when Mars is near its farthest point from Earth, that delay grows to more than 20 minutes each way, over 40 minutes round trip. Think about what that means in a real emergency. A crew member collapses, a system fails, a fire starts in the habitat module. The crew sends a message to Earth. 40 minutes later, they receive a response. By then, whatever was going to happen has already happened. The advice arrives after the crisis has resolved itself, one way or another. Real-time conversation becomes impossible. Mission control cannot guide a Mars crew through a problem the way Houston guided the Apollo 13 astronauts through theirs. Communication shifts from a phone call to something closer to sending letters. You write down everything you know, send it, and wait. The crew on Mars must diagnose the problem, consider the options, and make the decision themselves, long before any input from Earth can reach them. They are not remote controlled. They are autonomous, and that autonomy begins before they even land. Mars has an atmosphere, but here's where it gets strange. That atmosphere is almost useless. It is thin enough that it barely registers, roughly 1% of the density of Earth's atmosphere. You cannot breathe it. A parachute deployed in it would behave as if it had almost nothing to grab onto. And yet, it is thick enough to generate enormous heat during a spacecraft's entry. Dense enough to create friction, to push back, to burn. This is the atmospheric paradox of Mars. Too thin to stop a falling spacecraft. Too thick to ignore, both at once. Landing on Mars requires solving that paradox with a sequence of systems that must each work perfectly, in order, with no tolerance for failure. A heat shield absorbs the initial violence of atmospheric entry. Parachutes slow the descent to something survivable, though not enough on their own. Retro rockets fire in the final moments to bring the craft to a controlled touchdown. Each system hands off to the next. Each transition must succeed. There is no second attempt. There is no abort and try again tomorrow. The sequence works or it does not. And while all of this is happening, the crew can do almost nothing. The phase from atmospheric entry to surface contact lasts about 7 minutes. Engineers at NASA call it the 7 minutes of terror. During those 7 minutes, automated systems make thousands of decisions. Sensors fire, valves open and close, engines ignite on precise schedules, calculated months earlier on Earth. The crew sits inside a vehicle they cannot meaningfully steer, trusting systems built and tested on Earth to function correctly in an environment those systems have never actually experienced. Mission Control on Earth watches the telemetry, but they are not watching in real time. By the time the signal crosses the distance to Earth, those 7 minutes are already over. The spacecraft has either landed or it has not. Whatever happened without anyone on Earth being able to intervene. They are observers, witnesses after the fact. Put all three things together: the distance, the communication delay, the landing physics. They form a single, quiet conclusion. Earth cannot rescue a Mars crew. Earth cannot guide a Mars crew through a crisis in real time. And Earth cannot reach a crew that did not survive entry. From the moment a Mars mission leaves Earth orbit, the crew is on its own in a way that no human crew in history has ever been. That was only the first layer of what makes a Mars mission categorically different from anything that came before. The isolation that begins in transit does not end when the crew lands. On the surface, it deepens. Now suppose they do land safely. The vehicle sits still on the Martian surface. The dust settles. The crew is alive. And the question that was always waiting beneath the question of getting there rises to the surface. How do they come home? This is where most people assume the hard part is already over. The thinking goes, if you can get to Mars, you can get back. The same way you arrived, in reverse. But that assumption collapses the moment you examine it. The spacecraft that delivered the crew to the surface cannot bring them home. Not because of a design flaw, not because of a cost decision, because physics will not allow it. A lander descends through the Martian atmosphere, burning fuel the entire way. By the time it touches down, nearly everything it carried for propulsion has been spent. There is nothing left for an ascent. The lander is, at that point, a habitat, a shelter. It is not a vehicle anymore. It will never leave the surface. It will sit there until Mars reclaims it. So the crew needs a separate vehicle entirely. A Mars ascent vehicle built solely for the purpose of lifting them from the surface, reaching Martian orbit, and beginning the journey back. And here is the first layer of the problem. That vehicle cannot arrive with the crew. It has to be sent ahead, landed on Mars before the crew departs Earth, and left waiting. Alone. On the surface. For months. Sometimes for years. Think about what that vehicle must endure while it waits. Mars swings between temperatures of negative 125 degrees Celsius in its winter, at high latitudes, and positive 20 degrees Celsius on a warm afternoon. That is a range of 145 degrees within a single world. Mechanical components expand and contract. Seals degrade. Lubricants stiffen or fail. Dust storms capable of covering the entire planet in suspended particles work their way into every gap and bearing surface. Radiation streams in without the shielding of a strong magnetic field or a thick atmosphere to absorb it. And the ascent vehicle sits through all of this, unmanned, unmonitored in any meaningful real-time sense, waiting to function perfectly on the day a crew's survival depends on it. That alone would be a formidable engineering challenge. But the deeper problem is not the waiting, it is the fuel. To understand what a crewed Mars ascent vehicle actually requires, it helps to look at the most powerful rocket humanity has ever built and use it as a reference point. The Saturn V, the vehicle that carried Apollo astronauts to the moon and back, stood nearly 110 meters tall and weighed approximately 2,800 metric tons when fully fueled. That is about 6.1 million pounds. Of that total mass, approximately 2,600 metric tons was fuel. Propellant. The chemical energy needed to push everything off the ground and through the sky. When you do that arithmetic, roughly 93% of the Saturn V's entire mass was fuel. The vehicle, the engines, the crew capsule, the astronauts, the equipment, the life support, all of it together accounted for only about 7%. And after all of that force, after burning through 2,600 metric tons of propellant, what reached the moon and came back? Approximately 43 metric tons. The command and service module, the thing that mattered, 43 metric tons, from a starting mass of 2,800. That was for the moon, a body with 1/6 Earth's gravity, no atmosphere. Mars is harder. Significantly harder. Mars' gravity is about 38% of Earth's. That is weaker than Earth, but more than 6 times stronger than the moon's. A rocket lifting off from the Martian surface is fighting real gravity, the kind that demands serious thrust over a sustained burn. And Mars has an atmosphere, thin as it is. Thin enough that it was almost useless during the descent, and had to be overcome by other means. But thin is not zero. During ascent, that atmosphere creates drag. It is something the rocket has to push through. The moon offered neither of those obstacles. Mars offers both. The result is that a crewed Mars ascent vehicle would need to be comparable in scale to the rockets we currently use to lift payloads from Earth's surface. Not a small capsule perched on a modest booster. Something closer to the class of vehicle SpaceX builds to reach orbit from a planet with full Earth gravity and a dense atmosphere. Now, think about the mass cycle that creates. If the ascent vehicle requires, as a rough working figure, roughly 30 to 50 metric tons of propellant to lift a crew off Mars and reach orbit, that fuel has to come from somewhere. If it comes from Earth, it must survive the transit to Mars, the orbital insertion, and then the landing sequence onto the Martian surface. Landing that much propellant requires more propellant for the landing itself, which means a heavier vehicle departing Earth. which requires more launch fuel, which means a heavier vehicle sitting on the launch pad. The cycle does not simply add costs linearly, it compounds. Each extra kilogram of mass you try to bring to Mars demands additional fuel at every stage of the journey, and that fuel demands additional fuel to carry it, and so on, spiraling outward in every direction. The mathematics close off quickly, not as a near miss, not as a problem requiring modest engineering refinement. The numbers simply do not work. Supplying a Mars ascent vehicle with fuel from Earth is mass prohibitive in a fundamental sense. You cannot get there from here, no matter how you redesign the vehicle or reroute the supply chain. The compounding mass penalty eventually exceeds anything a reasonable launch architecture could accommodate, which means the fuel cannot come from Earth. It has to be made on Mars. That is not a workaround. It is not a fallback plan for when the conventional approach fails. It is a hard prerequisite. Before a single human can return from Mars, someone or something has to figure out how to manufacture rocket propellant on the surface of another planet using resources already present there. The ascent problem does not wait at the end of the mission. It sets the conditions for whether a return mission is even conceivable. And how to actually produce that fuel on Mars, and what it would take, is a problem that opens up an entirely different set of challenges. There is another way to think about this problem. If the fuel cannot come from Earth, the only remaining question is whether it can come from Mars. And that question, it turns out, has an answer. Not a speculative one, not a theoretical one waiting on future science. An answer that has existed, quietly and completely, since 1897. Start with what Mars has in abundance. The Martian atmosphere is 95.3% carbon dioxide. Nearly all of it. Breathe in on the surface of Mars and you would take in almost nothing but CO2. That sounds like a liability. From a propellant manufacturing standpoint, it is a feedstock. A raw material present in enormous quantities, requiring no mining, no drilling, no complex extraction. The atmosphere is simply there, pressing down at every point on the planet's surface, waiting to be used. Water is the second ingredient, and Mars has that too. Not liquid water on the surface, but ice. Water ice locked into the soil at high latitudes, and concentrated in permanently shadowed craters near the poles where the sun never reaches. Extracting it requires either heating the soil until the ice sublimes out, or drilling into the deposits directly. Neither approach is simple, but the resource exists. Mars has not one but both of the raw materials the chemistry requires. Here is where the chemistry begins. You take the water ice you have extracted, and you run an electrical current through it. This process is called electrolysis, the splitting of water molecules using electricity. The equation is simple. 2 molecules of water become 2 molecules of hydrogen gas, and 1 molecule of oxygen gas. The oxygen is one of the 2 propellants you need. Liquid oxygen is half of the fuel combination that can lift a rocket from the Martian surface. Set it aside in cryogenic storage and hold it. The hydrogen goes somewhere else. This is where a French chemist working in a university laboratory in 1897 enters the story. His name was Paul Sabatier. He was studying the behavior of gases in the presence of metal catalysts, and he discovered something that at the time seemed modest in its implications. If you combine carbon dioxide with hydrogen in the right conditions, with a nickel catalyst and heat, they react together. The carbon dioxide and the hydrogen do not simply mix, they transform. 4 hydrogen molecules combine with 1 carbon dioxide molecule, and what comes out the other side is methane and water. The equation is this: CO2 plus 4 H2 yields CH4 plus 2 H2O. Carbon dioxide plus hydrogen yields methane and water. Methane is rocket fuel. Specifically, it is the fuel half of a methane-oxygen propellant combination. The same combination, it happens, that certain next-generation launch vehicles on Earth are already designed to burn. Sabatier did not know any of this. He was interested in chemistry, not spaceflight. He published his findings, won the Nobel Prize in Chemistry in 1912 for unrelated but related catalysis work, and his reaction became a useful industrial tool. For over a century, it sat in textbooks and industrial processes, doing quiet, useful work. And then engineers designing crude Mars return missions looked at the problem of propellant manufacture and found that a 19th century French chemist had already written the solution, not a partial solution, not a framework requiring new science to complete. The mechanism was already there, mature, tested, well understood. The answer was stranger than expected. Look at the reaction again. CO2 plus 4 hydrogen molecules yields methane and water. The water that comes out of the Sabatier reaction can be fed directly back into the electrolysis step. The electrolysis splits that water into more hydrogen and more oxygen. The hydrogen goes back into the Sabatier reaction. The oxygen joins the growing store of oxidizer. The cycle continues. What this means is that once you have a source of carbon dioxide, the loop is effectively closed. The water gets used, recycled, and used again. The only continuous input the system requires after the initial water extraction from Martian soil is carbon dioxide from the Martian atmosphere, and Mars provides that in nearly limitless supply. The methane and oxygen produced through this chain must then be cooled into liquid form for storage. Liquid methane stays liquid at around minus 161 degrees Celsius. Liquid oxygen requires minus 183 degrees Celsius. Both of those temperatures are colder than anything Mars experiences naturally. The coldest Martian nights, in the depths of winter near the poles, approach minus 125 degrees Celsius. They do not reach minus 161. They certainly do not reach minus 183, which means the storage tanks cannot rely on the ambient Martian environment to keep the propellants cold. Active refrigeration systems must run continuously, consuming power, generating heat that has to be managed, adding mechanical complexity to hardware that must operate unattended for months. And this is where the problem that felt solved begins to reopen. The Mars ascent vehicle cannot wait for a crew to arrive before it starts making fuel. The fuel has to be ready before the crew leaves Earth. The manufacturing process runs ahead of the mission, sometimes by a year, sometimes by more. And during all of that time, the liquid methane and liquid oxygen sitting in insulated tanks on the Martian surface are slowly, continuously trying to return to their gaseous state. This is called boil-off. Cryogenic propellants are not stable in the way a can of paint or a battery is stable. They push back against containment. Even with insulation and active cooling, a fraction of the propellant evaporates. How large a fraction depends on tank design, insulation quality, power availability, and the length of the storage period. The exact losses across a multi-year storage window on Mars are not fully characterized. The uncertainty is real. What the Sabatier process gives you is not a finished solution. It is a viable path where no viable path existed before. The chemistry works, the loop closes, the feedstocks are present on Mars. A reaction discovered in a French laboratory more than a century ago by a chemist studying something else entirely turns out to be the keystone of human return from another planet. That is a striking thing to sit with. Not the story of a breakthrough engineered for space, the story of knowledge waiting, complete and patient, for a problem that would eventually need it. But manufacturing the propellant is only part of what has to happen before the crew arrives. The fuel has to be made, stored, kept cold, and protected across a waiting period that may stretch years. And the hardware that does all of this has to land, power up, and operate on Mars with no one present to intervene if something goes wrong. Of course, none of that chemistry runs without power. The Sabatier reaction needs heat. The electrolysis unit needs current. The cryogenic refrigerators keeping liquid methane and liquid oxygen from boiling away need continuous electrical draw. Every sensor, every valve, every pump in the system needs power. And producing 30 to 50 metric tons of propellant over 18 to 24 months requires somewhere between 100 and 200 kilowatts of continuous electrical output. Think about what that number means. 100 to 200 kilowatts is the continuous draw of roughly 70 to 140 average American homes, running without interruption for months, on a planet with no power grid, no transmission lines, no utility infrastructure of any kind. So where does the power come from? The obvious answer is solar. Sunlight reaches Mars. The technology is proven. Solar panels have powered spacecraft for decades. But Mars is farther from the Sun than Earth is, and that distance matters in a specific, measurable way. At Earth's distance, sunlight delivers about 1,368 watts per square meter. At Mars's average distance, that figure drops to about 590 watts per square meter, less than half. And that is before accounting for the day-night cycle, the seasons, the angle of the sun in the Martian sky, and the fine reddish dust that coats every exposed surface over time. To generate 100 to 200 kilowatts from solar panels on Mars, accounting for those reductions and inefficiencies, you would need several thousand square meters of panels. That is a significant installation. But the geometry problem is not the worst of it. The worst of it is the dust. Mars has dust storms. Local storms are common. Regional storms sweep across entire hemispheres. And global dust storms, covering the entire planet, occur roughly every 3 to 4 Martian years. During a global storm, suspended particles can reduce surface sunlight by 50 to 99%. Not a modest reduction. In some cases, nearly total darkness at the surface, lasting weeks. Here is what that means in practice. In 2018, a global dust storm swept across Mars. A rover called Opportunity was operating on the surface at the time. Opportunity was solar-powered. The storm blocked enough sunlight that its panels could no longer maintain the battery charge needed to run its heaters. Without heat, the electronics grew too cold to function. The rover froze. It never woke up. Not a hypothetical failure. Not a modeled risk. A documented outcome on actual hardware on the actual Martian surface. A fuel plant depending on solar power faces that same vulnerability. A global storm arriving during the production window does not merely slow output, it stops it entirely. And unlike a rover, which can lose weeks of driving data without catastrophic consequence, a propellant plant on a deadline cannot simply pause. Every day of production lost is a day the crew's departure window shifts. Enough lost days and the window closes. But here's where it gets strange. The more reliable power option is one that triggers a different set of concerns entirely. Nuclear fission reactors do not care about dust storms. They generate power from radioactive decay, not from sunlight. A reactor running on Mars produces the same output on the darkest day of a global storm as it does under clear skies. NASA has already developed a working design called kilopower, a uranium fission reactor roughly the size of a trash can that produces 10 kilowatts of continuous electrical output. The technology works. The physics are well understood. The Soviet Union operated nuclear reactors at remote Arctic bases for decades, unmanned, in one of Earth's harshest environments. The concept of unattended nuclear power in a hostile location is not new. But reaching the scale needed for a Mars propellant plant requires either 10 to 20 kilopower units running in parallel, or a single larger reactor producing 100 kilowatts or more. And every one of those reactors has to be launched from Earth. That means a rocket carrying live nuclear material. A launch failure, under the wrong conditions, could scatter radioactive material over a wide area. The risks are manageable. Engineers have designed containment systems for exactly this scenario. But the political and regulatory process surrounding a nuclear launch is not a technical problem. It is a social one, and social problems do not have clean engineering solutions. There is also a cooling problem specific to Mars. On Earth, nuclear reactors are cooled with water. Water carries heat away from the core efficiently and in large quantities. On Mars, water is scarce and mostly frozen. Running liquid coolant loops is impractical. The reactor must shed heat by radiating it into space, the same way a glowing coal radiates heat into the air around it. That requires large heat radiator panels deployed and operating continuously, more hardware, more surface area, more mass that had to be landed and assembled. And all of this brings us to the problem underneath the power problem. Everything described so far must run on its own. Not with a technician checking readings each morning, not with a repair crew on standby. On its own, for months or years, before a single human being sets foot on Mars. The fuel plant is not a machine you run. It is a machine you send ahead and trust. The systems monitoring that plant make thousands of decisions every day. Temperature readings feed into valve positions. Pressure readings adjust pump speeds. Power levels shift between subsystems depending on demand. Control software manages all of it, continuously, with no operator present. Maintenance robots will need to clear dust from panel surfaces, replace worn components, re-establish failed connections. Every function that a human technician would perform at an Earth-based facility has to be performed autonomously by hardware that was designed and programmed before anyone knew exactly what conditions it would encounter. And the conditions are severe. At the equator, a summer day on Mars can reach positive 20 degrees Celsius. That is a comfortable temperature. But the same night, the same location, drops to negative 73 degrees, nearly 100 degrees of swing between afternoon and midnight. At higher latitudes, or during winter, temperatures fall to negative 125 degrees Celsius. The total cycling range exceeds 200 degrees day after day for years. Most materials do not survive that gracefully. Rubber seals crack in cold that deep. Lubricants freeze and lose viscosity. Batteries discharge faster and recover less completely at low temperatures. Electronics behave unpredictably when temperature swings exceed the range they were designed for. A component that passes every lab test at controlled temperatures may fail on the 40th thermal cycle on Mars, or the 400th. Radiation adds another layer of continuous damage. Mars has no global magnetic field. Its atmosphere, at roughly 1% of Earth's density, blocks very little. Cosmic rays and solar radiation reach the surface with minimal filtering. Over months and years, that radiation causes bit flips in digital memory, the kind of error where a stored number changes by a single digit, and a valve that should open stays closed. It degrades solar panels, reducing their output incrementally with each passing month. It embrittles plastics and composite materials, making them stiffer and more prone to cracking. Shielding reduces the damage, but shielding has mass, and every kilogram of shielding added to the plant is a kilogram that cannot be payload, cannot be fuel, cannot be spare parts. The mass trade-off is constant, and it runs in every direction. What all of this means in practice comes down to a single number. The target is 50 metric tons of propellant, roughly the mass of 35 automobiles, sitting in cryogenic tanks and waiting for the crew to arrive. To reach that figure, the plant must produce somewhere between 100 and 200 kilograms of propellant per day. At that rate, filling the tanks takes 9 to 18 months of continuous, uninterrupted operation. Any breakdown extends that timeline. A sensor failure, a pump seized by cold, a power fluctuation during a dust storm, a bit flip that sends a wrong instruction to a valve. Each one pushes the calendar further out, and the crew's departure window does not move to accommodate the delay. It simply gets closer, and then it passes. That is the operational reality underneath the chemistry. And the environment that makes the chemistry difficult is the same environment the crew will have to survive once they arrive. Step back from the propellant plant for a moment. Step back from the cryogenic tanks and the dust storms and the autonomous control software managing thousands of daily decisions. The engineering problems are real, but behind every engineering problem is a funding problem. And behind every funding problem is a question no one in the space program likes to answer directly. How much are we actually willing to spend? To answer that, you need a baseline. You need something we already built, already paid for, already flew. You need Apollo. The Apollo program cost $25.8 billion between 1960 and 1973. That number sounds manageable until you translate it into today's money. In today's dollars, Apollo cost roughly $280 billion for 12 people on the moon. Think about what those 12 people accomplished. 6 missions, roughly 9 days of total surface time across all 6, with the longest single mission reaching about 12.5 days on the lunar surface. 9 days for $280 billion in today's money. That was not a small program. At its peak in 1966, the Apollo program employed more than 400,000 people. Engineers, technicians, contractors, manufacturing workers spread across dozens of facilities. At that peak, NASA's budget represented more than 4% of all federal spending. Today, NASA's budget is less than half of 1% of federal spending. The scale of Apollo was not normal. It was a national emergency treated as a moonshot because that is exactly what it was. The physical infrastructure reflected that scale. The Saturn IV required entirely new manufacturing facilities. Rockets that large had never been built. Buildings that large had barely been built. The Vehicle Assembly Building at Kennedy Space Center, constructed specifically for Saturn V assembly, remains one of the largest structures by volume anywhere in the world. Tracking stations were built on Pacific and Atlantic islands, positioned specifically to maintain contact with missions crossing those oceans. None of this existed before Apollo. All of it had to be created. And here is the thing about that infrastructure. It was built for missions 3 days from Earth. 3 days to the moon and 3 days back, with communication delays measured in seconds. With Earth's gravity a short burn away. With the option of a fast return in genuine emergencies, that option was used. In April 1970, Apollo 13 suffered an oxygen tank explosion 2 days after launch. The crew of 3 had a lunar module designed to support 2 people for 2 days. They used it for 4 days. They improvised carbon dioxide scrubbers from lithium hydroxide canisters, duct tape, and plastic bags, because the scrubber canisters from the command module were the wrong shape to fit the lunar module's system. The cabin temperature dropped toward freezing. The crew survived on rationed water and no sleep. They came home. They came home because they were 3 days away. The return path existed. The fuel to take it had not been expended. Mission Control could communicate in real time, iterate on the improvised scrubber design in real time, guide the crew through every step in real time. The distance was forgiving enough to allow for improvisation. Now consider the mass those missions carried. The Apollo Command and Service module weighed about 32 metric tons. The lunar module weighed about 15 metric tons. Together, roughly 47 metric tons of spacecraft delivered a crew to lunar orbit and brought them home, with the lunar module supporting surface operations for less than 2 weeks at most. A Mars transit vehicle would need to be several hundred metric tons, fully loaded. The transit alone takes 6 to 9 months each way. The vehicle must carry food, water, air, radiation shielding, and all the redundancy that a 6-month journey with no resupply option demands. The Mars lander and surface habitat add another 100 metric tons or more. And then there is the ascent vehicle, the fuel plant, the power systems, the rovers, all pre-positioned before the crew ever leaves Earth. More mass requires more fuel. More fuel requires larger rockets. Larger rockets require more fuel to lift the fuel. The compounding runs in every direction, just as it did when we mapped it through the Saturn V. What changes at Mars scale is how far the compounding runs before it stops. A baseline single-plant Mars mission, using one propellant production facility and accepting the single-point failure risk that implies, costs in the range of $50 billion even under optimistic assumptions. Add 2 more parallel plants, sent on separate cargo missions, landed at separate sites, insured against the failure modes we have now spent 4 sections cataloguing. The figure rises to $70 or $80 billion. That is for the propellant production infrastructure alone. It does not include the transit vehicle. It does not include the crew systems. It does not include the ascent vehicle. It does not include the surface habitat, the power systems, the communications infrastructure, the medical equipment, or the years of ground support. Those costs compound on top. Wait, this is worth sitting with. The redundant propellant infrastructure for a Mars round-trip mission, built to the standard we know is necessary, costs 2 to 3 times what the entire Apollo program cost in today's dollars for one mission. Not slightly more expensive. Categorically more expensive. And Apollo had 400,000 employees, a NASA budget that consumed more than 4% of federal spending, and the Cold War as its justification for public funding at that scale. The question underneath all of this is not purely technical. It is not whether the chemistry works, whether the reactors can be built, whether the software can manage the autonomous operation. Those are hard problems with potential paths forward. The question underneath is whether any democratic society, balancing competing priorities, will sustain the level of funding required to build and fly a round-trip mission over the decade or more that such a mission would require to develop. That is the cost trap. The engineering response to every failure mode is redundancy. Redundancy multiplies cost. Cost runs into the limit of what societies will actually sustain, not what they will theoretically endorse. Apollo reached that limit at 12 people and 9 days of surface time, and Apollo had a geopolitical crisis driving it. There is a version of Mars exploration that fits inside a funding envelope societies have historically been willing to maintain. That version looks very different from a round-trip mission, but that version has its own set of consequences. And those consequences are what the rest of this changes. The cost is not only financial, it lives in the body, it lives in the mind, it accumulates across every hour of every day of a mission that, once committed to, cannot be shortened. Here is something that does not come up often enough in the conversation about Mars. Even after a perfect landing, even after the propellant plant has run without incident, and the Mars ascent vehicle is sitting fully fueled and ready, the crew cannot leave. Not for months, not for nearly 2 years. Earth and Mars move in long, slow arcs around the Sun, and they only realign into a viable return geometry every 26 months. Miss that window and you wait another 26 months. The minimum surface stay is approximately 730 days. That number is not an engineering estimate, it is an orbital fact. The crew lands, they look at each other, and they know. They are staying for 2 years. There is no early departure. There is no change of plans. So the question becomes what those 730 days actually cost the people inside them. The first thing to understand is the environment. The habitat would be a few connected pressurized modules. From the inside, it would feel something like a long submarine or a very cramped research station. Every time a crew member steps outside, they wear a heavy, bulky suit because the Martian atmosphere cannot support human life for even a moment without it. There is no feeling of wind, no rain, no smell of earth or grass or anything alive. The sky from the surface is a muted reddish-brown, not blue, and the light has a quality unlike anything on Earth. Research on confined analog environments, including Antarctic stations and long-duration submarine deployments, shows that the threshold for significant psychological stress in isolated, confined settings is roughly 6 months. By that point, irritability increases, sleep disrupts, depression begins to take hold, cognitive performance declines in measurable ways. The Mars crew would cross that threshold and then keep going. They would cross it and then live inside that territory for more than a year beyond it. But the reality was different. The psychological burden would not arrive as a single breaking point. It would accumulate. A slow, grinding pressure across months of sameness. The same walls, the same faces, the same recycled air, the same narrow view through a small porthole of a landscape that does not change. Humans did not evolve for this, and no amount of preparation fully counteracts it. Meanwhile, the body is changing. Mars' gravity is 38% of Earth's. Not zero gravity, like the International Space Station, but not the full pull of home either. On the ISS, astronauts lose between 1 and 2% of their bone mass every month, despite spending 2 hours a day on exercise equipment specifically designed to slow that loss. The exercise works, but it does not stop the process. On Mars, the partial gravity helps. The loss is slower, but the duration is so much longer. Over a 2-year surface stay, the projected cumulative bone density loss could reach 20 to 30%. That is not a minor degradation. That is a body that has fundamentally changed. And bones are not the only concern. Muscle mass erodes, cardiovascular fitness shifts. The crew arrives changed, returns more changed, and must then readapt to Earth's full gravity after 2 years of living in a fraction of it. Then there is the question of medicine. An appendicitis is routine on Earth. A patient goes to a hospital, a surgical team prepares, an anesthesiologist manages sedation, a blood bank stands by, and the procedure is performed. Recovery takes days. On Mars, that same appendicitis becomes a life-threatening emergency with no clean solution. A crew of 6 to 8 people cannot cover all the medical specialties those capabilities require. You need doctors and engineers and geologists and system specialists, and you cannot carry them all. You cannot include a dentist, a radiologist, an anesthesiologist, a surgical nurse, and still have room for the people who keep the habitat running and the mission functioning. So some of those specialties are absent, and telemedicine cannot close the gap. At its best, the round-trip signal delay is 20 minutes. At its worst, it is closer to 40. A real-time conversation with a surgeon on Earth is physically impossible. The doctor on Mars receives guidance that was sent 20 minutes ago in response to a situation that may have changed significantly since. They operate on training, written procedures, and personal judgment. They have to. There is no other option. And radiation is running the entire time. On Earth's surface, a person absorbs roughly 3 millisieverts of radiation per year. On Mars, with its thin atmosphere and absent magnetic field, that figure rises to approximately 240 millisieverts per year. A 2-year surface stay accumulates roughly 480 millisieverts from surface exposure alone, before accounting for the transit to and from Mars. NASA's current crewed mission safety limits would be exceeded. The risk is not immediate. Radiation damage of this kind expresses itself decades later, in elevated cancer rates, in cellular changes that build quietly over years before becoming visible. The crew would not feel it on Mars. They would carry it home with them and spend the rest of their lives inside the increased probability it created. Wait, that is worth pausing on. A crew that executes the mission flawlessly, that encounters no equipment failures, no emergencies, no accidents of any kind, still returns to Earth having absorbed a radiation dose that exceeds what their own space agency considers acceptable for a human being. Not because something went wrong, because the mission went exactly as planned. And this is all before accounting for what happens to the habitat itself. Mars's atmosphere is too thin to burn up most incoming debris. Micrometeorites that would vaporize harmlessly in Earth's atmosphere can strike a Mars habitat at full velocity. A large enough strike causes depressurization. A habitat loses pressure in minutes. The crew has minutes to respond, to seal the breach, to don suits, to improvise what they can. And the critical systems of the habitat are each their own countdown clock. Without functioning oxygen generation, the crew has minutes. Without functioning carbon dioxide scrubbers, they have hours, perhaps a day or two before CO2 builds to lethal levels. Without water recycling, they have days. Every one of those systems must run without failure, day after day, for 730 days. The Apollo 13 crew improvised a carbon dioxide scrubber from materials on hand, and brought their spacecraft home. That kind of problem solving, that resourcefulness under pressure, saved 3 lives. But Apollo 13 lasted less than a week from the explosion to splashdown. The Mars crew would need to sustain that level of resilience, that capacity for improvisation under mortal pressure. Not for days, but for years. Every system failure is an Apollo 13, and they keep coming. The orbital mechanics still trap them. The radiation still accumulates. The bones still thin. The mind still strains against the walls. Even the mission that succeeds leaves its mark on the people who flew it. And those marks do not disappear when the capsule splashes down. Those marks travel with them through the return transit, through the months of readaptation, through the rest of their lives. And at the far end of all that, waiting back on Earth, are the same mountains, the same crowds, the same gravity pulling down on bones already changed by 2 years of something lighter. The mission ends. The damage does not. So consider a different question. Not how do we bring them home, but what if we stopped requiring it? The question feels radical at first. It dissolves the moment you follow the engineering. Almost every element of a crewed Mars mission that is brutally expensive, technically unresolved, or catastrophically risky is tied to one requirement: the return. Remove that requirement and watch what happens to the problem. The ascent vehicle disappears from the mission architecture. The propellant plant built to manufacture 30 to 50 metric tons of fuel for that ascent vehicle disappears with it. The mass of that plant, the power systems running it, the autonomous maintenance hardware keeping it operational across years of unattended operation, the cryogenic storage tanks, the active refrigeration, all of it goes. The 6 to 9 month return transit vanishes. The life support systems designed to keep a crew alive for that additional transit vanish with it. Every kilogram freed from those requirements can go towards surface supplies, habitat redundancy, medical equipment, instruments, and additional crew capacity. The mission does not just get cheaper, it gets simpler. And in engineering, simpler is safer. The cost shift is not marginal. A round-trip crewed Mars mission with the redundant propellant infrastructure required to approach reliable safety runs into the hundreds of billions of dollars. By some projections, the full architecture approaches $1 trillion across the mission lifetime. A one-way mission, by serious estimates, drops into the tens of billions. That difference is not a rounding error. That is the difference between a mission that strains the outer boundary of what any democratic government will sustain across a decade of development and a mission that fits inside a historically recognizable funding envelope. And with existing technology, a one-way mission is achievable within 10 to 20 years. Not with breakthroughs waiting in laboratories, not with propulsion systems that do not yet exist, with focused development of what is already understood. The commitment is the missing ingredient. But here is where the question shifts in a more important way. One way changes what the mission is. A crew that cannot return is not a crew of explorers visiting a destination. They are settlers establishing a presence. The mission goal is not to visit Mars and return with data. The mission goal is to build the first permanent human foothold on another world. The colonists are not tourists. They are the colony. That reframing matters because it changes what counts as success. A round-trip mission succeeds when the crew comes home. A one-way mission succeeds when the outpost survives, grows, and eventually stops needing resupply from Earth. Those are different objectives and they produce different engineering priorities, different crew profiles, and different definitions of sacrifice. The obvious question follows immediately. Who would accept those terms? In 2012, a private organization called Mars One was founded in the Netherlands by an entrepreneur named Bas Lansdorp. The proposal was straightforward and, to most observers, implausible. A one-way mission to Mars, funded through a global media event, staffed entirely by volunteers who understood they would not be coming home. Mars One put out a call for applicants. More than 200,000 people responded. From more than 140 countries, not a handful of thrill seekers, not a fringe community. 200,000 people screened through a public application process, who read the terms and submitted their names. Mars One declared bankruptcy in 2019. No hardware was ever built, no launch contracts were ever signed. The organization's financial model and technical ambitions exceeded its actual capacity. But the 200,000 applications were real, and they answered a question that most people assumed had an obvious answer. The assumption was that no one would willingly accept a one-way trip to Mars. The application said otherwise, not theoretically, not as an abstraction. 200,000 people in writing with their names attached. This is not unprecedented. History is full of it. In 1620, the Mayflower carried approximately 100 passengers across the Atlantic. Most of them understood they were probably not going back. The voyage itself killed nearly half the colonists in the first winter. People kept coming. For decades, ships carried settlers who had made the same calculation, weighed the same uncertainty, and decided that what waited on the other side was worth the cost of not returning. The Oregon Trail in the mid-1800s was not a round trip. Families loaded everything they owned onto wagons and walked for months across terrain that killed a significant fraction of them. They went anyway, not because they did not understand the risk, because they had decided the destination mattered more than the guarantee of return. In 1914, Ernest Shackleton prepared an expedition to Antarctica. He placed an advertisement in British newspapers that has since become one of the most quoted in history. The language was stark. Men wanted for hazardous journey, low wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful. The advertisement received more than 5,000 applications. There were 28 positions. 5,000 people applied for 28 seats on a journey described as dangerous, miserable, and probably fatal on the return leg. The bottleneck was never human willingness. It has never been human willingness. The bottleneck is engineering and funding. What the selection process for a one-way Mars mission would need to do is identify which people from that enormous volunteer pool are actually suited to the task. Technical skills are the floor, not the ceiling. Medical knowledge deep enough for basic surgery and emergency treatment. Engineering competence sufficient to repair and improvise with habitat systems. Agricultural skills for greenhouse cultivation in a controlled environment. Geology and field science, rover and drone piloting, construction capability using whatever local materials the surface can provide. But the technical requirements, demanding as they are not the hardest part. Data from Antarctic research stations, long-duration submarine deployments, and years of International Space Station operations all point to the same finding. In isolated, confined environments over extended periods, the dominant threat to mission success is not system failure. It is interpersonal conflict. Small irritants compound across months. Personality friction becomes mission-threatening friction. The crew of a one-way Mars mission would need to function as a stable, cooperative unit, not for a deployment but for the rest of their lives. Psychiatric screening would be mandatory and rigorous. Depression, anxiety, and other vulnerabilities that isolation and confinement reliably exacerbate would need to be identified before selection. But psychological evaluation can identify vulnerabilities. It cannot guarantee multi-decade resilience in an environment that has no historical comparison group. No one has ever done this before. What holds a crew together across that kind of duration is not just compatibility, it is shared purpose. The early colonists who crossed the Atlantic in the 1600s were often held together by religious conviction. Their hardship had a framework. It meant something within a larger story they all believed. The Mars crew would need a comparable binding commitment. Not religious necessarily, but something of the equivalent weight. The conviction that establishing a permanent human presence on another world is worth their lives, worth the absence of everything they left behind, worth the certainty that they are not coming home. Training for that mission would take 5 to 10 years, depending on starting backgrounds. Analog environments exist. The Mars Desert Research Station in Utah, the Flashline Mars Arctic Research Station in the Canadian Arctic, volcanic regions in Iceland, high-altitude deserts in Chile. None of them replicate Mars fully. The gravity is wrong, the atmosphere is wrong, the radiation is absent, but they are the closest available approximation, and they teach something real about confined cooperation under physical stress. Psychological support would be available within the limits of the communications delay. A counselor on Earth can exchange messages with a Mars crew member. Those messages travel at the speed of light and arrive 20 minutes later, 40 minutes round trip at closest approach, longer when Mars and Earth are at opposite ends of their orbits. Therapy becomes correspondence. Support becomes letters with long pauses between them. The crew members would need to carry most of what sustains them inward, within themselves and within each other. 200,000 people already said yes. The engineering and the funding are the remaining questions. And those are questions we know, in principle, how to answer. Those questions about engineering and funding are real, but suppose they get answered. Suppose the hardware works, the propellant fills the tanks, the crew is selected and trained and ready. Suppose they have arrived. What does life actually look like on the other side of that journey? The habitat was already there when they landed. That is the design. The crew does not arrive at an empty planet and begin from scratch. Months before the crew leaves Earth, possibly years before, the surface modules are landed by automated systems. Solar arrays deploy, airlocks cycle, life support runs through its checks. Atmospheric processes start. The colony breathes before any human breathes inside it. When the crew finally sets down, close enough to walk in pressurized suits, but far enough that their landing debris does not damage the habitat, the structure is already tested and waiting. The first weeks are not dramatic in the way people imagine. There is no moment of planting a flag and standing back to admire it. There is unpacking. There is integrating redundant systems. There is testing, and testing again, and documenting what the tests showed, and testing once more. Routines form early because routines are survival. Every crew member knows which systems they're responsible for, which readings they check each morning, which numbers falling outside their expected range demand immediate attention. The habitat is small, 4 to 6 people. The corridors are narrow. The equipment takes up most of the space. In the early months, the novelty carries them. They are on Mars. No human being in the history of the species has stood where they are standing. That is not a small thing to know about yourself. It sustains a great deal. That is when the pattern broke. The novelty fades, not quickly, but steadily. The same butterscotch pink sky. The small and distant sun, dimmer than it looks on Earth, casting thin shadows across rust-colored rocks that do not change from one week to the next. No rain, no seasons in any way the crew recognizes. No new landscapes appearing as they walk. The horizon is always the same horizon. The same faces across the table every meal. The same food. The scientific work is real and it matters. Geology. Sample collection, drilling. Cataloguing rock layers that have been undisturbed for billions of years. The search for biosignatures, chemical traces or structural patterns in ancient sediment that would indicate life existed on early Mars when the planet was warmer and wetter. Meteorology. Testing technologies meant for future colonists who will arrive after them. This is meaningful work. But it is also work, which means it is also routine. The food deserves careful attention because it is not a secondary concern. It is the margin between survival and catastrophe. The greenhouse is a pressurized module, heated against the Martian cold, sealed against the thin atmosphere outside. The air inside is a nitrogen and oxygen mix, breathable, stable. Banks of LEDs, tuned specifically to the wavelengths plants use for photosynthesis, run on regular cycles of light and dark. The early crops are chosen for speed and yield: lettuce, spinach, radishes, tomatoes. These grow quickly and provide nutrition without demanding much space. Potatoes serve as the caloric backbone, dense with energy per square meter of growing area. Rice and wheat are possible in theory, but inefficient in practice. They demand space the colony cannot spare in its earliest years. The soil is Martian regolith, the loose, rocky surface material, processed. Raw Martian regolith is toxic to plants. It contains perchlorates, chemical compounds that are harmless in trace amounts, but lethal to plant biology in the concentrations found across much of the Martian surface. The perchlorates must be washed out before the soil can support anything. What remains gets supplemented with composted biological material, including human waste. Nothing is discarded. The colony operates on closed loops. Composting toilets break down biological material and return it to the soil. Pathogen control is critical at this stage, because the same closed loop that enriches the soil can also cycle illness through a crew of 6 with no easy way to interrupt the chain. Water comes from melted subsurface ice, purified, and then cycled back through the life support system. Every molecule is accounted for. The early nutrient supply comes partly from Earth stockpiles. The long-term goal is full self-sufficiency on Martian inputs. That goal remains unproven at scale. No one has yet grown enough food in processed Martian regolith over enough seasons to know with confidence that it will work indefinitely. Pause on this. That gap is worth naming clearly. The colony's agricultural system is not a solved problem brought to Mars. It is a living experiment running in real time, on which 6 people depend completely. If 2 or 3 crop cycles fail in sequence, emergency freeze-dried supplies cover the gap. But those supplies are finite. Continued failure means severe rationing while waiting for a resupply mission that is months away at best. The greenhouse is not a backup system. It is the system. Maintenance is the other constant. The work never stops and it never simplifies. Suits develop slow leaks at the joints. Dust clogs recyclers that filter the habitat air. Mineral deposits build up in water purification membranes. Solar panels lose efficiency as fine dust settles in layers that no wind is strong enough to clear. Batteries degrade with each charge cycle, holding less capacity than they did the month before. None of this is catastrophic on its own. All of it is continuous. The colony maintains workshops, tools, raw materials, spare components where spares exist, and fabrication capability where they do not. The crew can machine replacement parts. They can repurpose components from systems that have failed for other reasons to keep higher priority systems running. They can look at a broken piece of equipment and ask what it could become rather than what it was designed to be. This is the irreducible thing that humans bring to Mars that no robotic mission can replicate. Not just problem solving in the abstract. Improvisation sustained across years. Think about what that actually requires. Apollo 13 is the famous example, the moment when engineers on the ground and astronauts in space had to improvise a carbon dioxide scrubber from materials that were never intended for that purpose, under pressure, with the clock running. That took days. It was extraordinary. The Mars colonists would need to sustain that same quality of creative attention, not for days, but for the entire duration of the mission. Every failure that arrives without a pre-planned solution is a moment that demands the same thing Apollo 13 demanded. And the failures keep arriving. A robot sent to Mars can execute its program tasks with great precision. It cannot look at a failed valve and decide that a component from a different system could be adapted to replace it. It cannot notice that 2 separate small problems combined create a third problem that the original design never anticipated. It cannot improvise. The colonists can. That capacity is not incidental to the mission. It is the mission's core mechanism for staying alive. And that improvisation is not a temporary phase. It does not end when the systems mature. The colony is sustained by it, year after year, in ways that no pre-launch engineering plan fully captures. What makes the colony viable is not just what the crew brought with them. It is what they figure out after they arrive. A colony is more than its hardware. 6 people keeping each other alive across a Martian winter are also 6 people who eat together, argue about whose turn it is to clean the filters, fall asleep to the same recycled air, and wake up to the same rust-colored sky through the same small window. The machinery can be engineered in advance. The society cannot. A crew of 6 is too small for rigid hierarchy. That is not a philosophical preference. It is a practical reality. When every person holds skills the others do not have, when every person is simultaneously colleague and neighbor, and the only available help when something goes wrong, the chain of command flattens by necessity. Day-to-day decisions tend to settle by consensus. Who takes which shift, which repair gets priority, how much water the greenhouse gets during a shortage. These are conversations, not orders. There is a designated mission commander for emergencies, for the moments when a decision cannot wait for discussion. But most of the time, the colony operates more like a small research station than a military unit. And that means most of the tension is not dramatic. It is quiet. It is the kind that builds over months in a space where there is no way to get away from anyone. Hygiene habits in a pressurized habitat, noise at odd hours, comms bandwidth used when someone back on Earth is waiting and someone else is occupying the channel. The perception that one person is carrying more weight than another, whether accurate or not. These are small irritants. They do not feel like threats. But in a confined environment with no exit and no break in proximity, small irritants do not stay small. They accumulate. They become the texture of daily life. And they have brought down more isolated research teams than system failures ever have. This is why mission planners have increasingly accepted something that sounds almost mundane, alongside propellant chemistry and radiation dosimetry. Conflict resolution is a survival skill, not a soft one. Formal grievance meetings, scheduled and structured so that tension can surface before it calcifies. Practice communication frameworks so that frustration does not become resentment. The colony that cannot manage its internal social stress is as vulnerable as the colony with a failing water recycler. The difference is that a water recycler announces its failure clearly. Social fracture does not. The picture did not hold. The same planners who account for mechanical failure, radiation exposure, and crop shortfall have historically underestimated a different category of problem entirely: human relationships, physical attraction. The fact that in a mixed gender crew of healthy adults under extreme stress, bonds form that were not on any pre-mission schematic. This cannot be screened out of human nature. Some mission architects have proposed sending established couples, reasoning that stable partnerships reduce the unpredictability of new attraction. Others argue that Earth relationships frequently do not survive the pressures of long-duration missions, and that a partnership that collapses inside a habitat with no privacy and no separation is its own category of catastrophe. There is no clean answer. Both concerns are legitimate. Both point to the same underlying fact. The emotional lives of the crew are not separable from mission performance, and pretending otherwise is its own kind of planning failure. And then there is the question that planning documents have historically avoided with unusual consistency: pregnancy. In the earliest colony, pregnancy is regarded not as a natural consequence to be managed, but as a crisis. There are no obstetricians. There is no neonatal intensive care unit. There is no surgical theatre configured for a complicated delivery. The crew is already operating at the edge of its capacity. A pregnancy in the first months would redirect enormous resources toward a single event that the habitat was never designed to support. The effects of low gravity on fetal development are entirely unstudied. The effects of elevated radiation on a developing nervous system are not well characterized at Mars' surface exposure levels. No one knows what 38% of Earth's gravity does to a pregnancy across 9 months. No one has ever tested it. Later missions could be different. larger crews, more medical capacity, families sent intentionally as part of a long-term settlement architecture. But in the first years, the calculus is stark. The colony is not yet stable enough to absorb what a birth would demand. Eventually, though, the stability comes, and eventually, children are born on Mars. Think about what that generation experiences. They grow up in 38% gravity. Their bodies adapt to it from the beginning. Their musculoskeletal systems develop in it. Their cardiovascular systems calibrate to it. Not as an adjustment made from a different baseline, but as the only baseline they have ever known. Lower bone density than Earth-born humans. Lower muscle mass. A body shaped by a world 1/3 the gravitational weight of the one their parents came from. Earth is not home to them. Earth is a story, an image library, a place their parents came from described in terms that do not match anything visible through the habitat window. But here is where the reveal lands. If a Martian-born child tried to visit Earth, the physics would not cooperate. Moving from 38% gravity to full Earth gravity, that child would experience something close to tripling their effective weight overnight. A body that developed in 1/3 of Earth's pool, asked suddenly to function in the full pool, might not manage it. The cardiovascular system that grew up moving blood through a lower gravity circulatory demand would face a harder task than it was built for. The bones and muscles calibrated to Mars would be inadequate for Earth. Not strained, not uncomfortable, physiologically inadequate. These children cannot go back. Cannot in the sense of unwilling. Cannot in the sense of unable. Within a single generation, Mars produces a population that is irreversibly Martian, not by choice, by biology. The cultural divergence follows from this. Language drifts in any isolated community over time, and a community separated from its linguistic source by 40 minutes of communication delay drifts faster. New words arise for things that only exist on Mars. The texture of a dust storm, the quality of light when the sun is small and far, the specific silence of a pressurized room in a landscape that makes no sound. Grammar may shift in subtle ways that no one tracks deliberately, the way all living languages shift without announcement. The art produced on Mars will not look like Earth art. The rust deserts and pink sky are not a backdrop. They are the world. The literature will center on isolation and the act of building something where nothing was before. The music will be shaped by the acoustics of thin atmosphere environments and sealed rooms. A Martian culture does not need to be invented. It arrives on its own. And as it arrives, the political question becomes unavoidable. Early colonies operate under the authority of whatever agency or consortium sent them. NASA or SpaceX or an international coalition holding the contracts and the budgets and the mandate. That authority makes sense at the start. The colony depends entirely on Earth for resupply, for technical support, for the financial infrastructure that keeps missions coming. But the communication delay does not stay abstract. It becomes structural. When a decision must be made on Mars and the round-trip signal time is 20 to 40 minutes, Earth cannot govern in real time. By the time instructions arrive, the situation that prompted the question has already changed. The colony acts, and then informs Earth of what it did. Repeatedly. Over years. This is not insubordination. It is physics. But the practical effect is the same as autonomy. Mars presents Earth with accomplished facts. Earth cannot reverse them. A punitive expedition takes months to arrive and costs more than compliance is worth. The historical parallels are not subtle. American colonies maintaining local governance because London was too far to manage daily affairs. Australia moving from administered territory to independent nation across generations of practical self-governance. Antarctica, the world's most recent experiment in shared territorial management, governed today by a treaty that works as long as all parties agree it should. Mars will have its own version of this arc. A Martian declaration of independence could come decades after first landing. It could come centuries later. If Earth's demands become unreasonable, it could come sooner. No one can say when. But the structural conditions for it are baked into the mission from the beginning. The communication asymmetry is permanent, the physiological divergence is irreversible. The cultural distinctiveness accumulates with every generation that grows up knowing only one sky. The colony begins as an outpost. It becomes something else, without ever deciding to. And the children who cannot return to Earth will be the first generation that never needed to decide. Pull back further still. Pull back past the politics, past the children who cannot return, past the slow drift of a new language forming in pressurized rooms. Pull back, past the mission itself. Pull back to the question underneath all of it. Not why we are going, why we need to. Earth has been here for 4.54 billion years. Life has existed on it for roughly 3.8 billion of those years. Anatomically, modern humans have existed for about 300,000 years. Civilization, meaning cities and writing and agriculture and accumulated knowledge, is approximately 10,000 years old. Think about those numbers against each other. If Earth's entire history were compressed into a single calendar year, life appeared in late February. Humans appeared at roughly 11:37 on the night of December 31st. Everything we call civilization, every library, every city, every piece of recorded music, every scientific discovery, every language, every piece of art humanity has ever made, occupies the final 90 seconds before midnight. That is not a comfortable thing to sit with, but something was wrong. Earth has not been stable across those 4.54 billion years. It has not been a quiet, patient platform for life to develop without interruption. It has been catastrophically destabilized before, not once, repeatedly. 66 million years ago, an asteroid roughly 10 kilometers across struck the Yucatan Peninsula in what is now southeastern Mexico. The impact released energy equivalent to billions of nuclear weapons detonating simultaneously. The immediate blast was catastrophic. The longer consequence was worse. The impact threw so much debris and dust into the atmosphere that sunlight was blocked for months, possibly years. Temperatures dropped. Photosynthesis slowed. The food chains built on plant life collapsed from the bottom upward. Roughly 75% of all species on Earth went extinct. The dinosaurs, which had dominated terrestrial ecosystems for 160 million years, were gone. 160 million years. That is 16 times longer than the entire age of our civilization, and longer than the interval between that extinction and today. Not diminished, not reduced, gone. The Chicxulub impactor did not distinguish between common species and rare ones, between simple organisms and complex ones, between the adaptable and the specialized. It struck, and the consequences played out across a biosphere that had no mechanism to resist them. But that was not the worst extinction Earth has endured. 252 million years ago, at the boundary between the Permian and Triassic periods, something happened that nearly sterilized life from the planet entirely. The cause is still debated, possibly massive volcanic eruptions releasing enormous quantities of carbon dioxide, possibly an additional asteroid impact, possibly a combination of factors whose interactions amplified each other. What is certain is the result. Approximately 96% of all marine species went extinct. Approximately 70% of terrestrial vertebrate species were lost. The oceans became hot and oxygen depleted. Ecosystems that had taken hundreds of millions of years to build collapsed. Recovery took tens of millions of years. Not a disruption, not a setback. A near erasure, life recovered both times. That is the argument Earth's history offers. Given enough time, the biosphere rebuilds. But civilization cannot recover on geologic timescales. A mass extinction event that kills 75% of species does not spare the libraries. It does not preserve the accumulated knowledge of how to rebuild electrical grids, or how to synthesize medicine, or how to manufacture the components of a radio. It does not spare the art. The knowledge, the consciousness, the fragile ongoing conversation that humanity has been conducting with itself for 10,000 years is not stored somewhere outside the biosphere. It lives inside it. This is the argument for Mars that cannot be answered by mission engineering. The radiation shielding and the propellant plant and the food production systems are real problems that require real solutions. But they are not why humanity needs another world. The reason is older and simpler. Earthbound humanity is a single point of failure. Think about what that phrase means when you translate it out of engineering language and into geological time. It means that everything our species has built, everything it has learned, every piece of music ever written, every scientific discovery ever made, every language ever spoken sits on one planet, one surface, one atmosphere, one magnetic field between us and the particles the sun throws outward, one orbital path through a solar system still populated by objects large enough to end everything. A self-sustaining Mars colony changes that equation. Not because Mars is safe, it is not. Not because life on Mars would be comfortable, it would not be. But because a population of humans living independently on another world, growing their own food, manufacturing their own equipment, maintaining their own knowledge base, represents something that has never existed before in the history of life on Earth. A backup. The civilizational equivalent of copying critical data to a second location before the first drive fails. The threat does not have to be an asteroid. The list of civilization-ending scenarios that Earth's own history makes plausible is longer than that. A supervolcano releasing enough ash to trigger a global winter. A pandemic against which no immune system carries resistance. A nuclear exchange large enough to collapse the food chains that support 8 billion people. A runaway warming cycle that takes centuries to resolve, but takes civilization with it inside the first generation. None of these are science fiction. All of them have analogues in the geological record. The Chicxulub impactor is the famous one. The Permian-Triassic extinction is the devastating one. But the catalogue of near misses and partial disasters scattered across 3.8 billion years of life on this planet is sobering reading. What makes this moment unusual is that we are the first species in Earth's history that can do something about it. The dinosaurs had no option. They were exceptionally successful for 160 million years, and then the sky changed and they were gone. They had no spacecraft, no propellant plants running on captured atmospheric gases, no ability to recognize the threat before it arrived, no capacity to send a population somewhere else before the collision. We have all of those things, or we are within a generation of having them. The question is whether we will use them before we need them, rather than after. But the Mars story carries one more layer that the engineering case does not reach. Mars may not be a dead world. It may be a world that was alive. Billions of years ago, Mars was different. It was warmer. It was wetter. It had rivers cutting channels into its surface that are still visible from orbit. It had lakes. It may have had an ocean covering a significant portion of its northern hemisphere. It had a thicker atmosphere. And it had a magnetic field. The kind of field that shields a planet from the solar wind and holds an atmosphere in place. Then something changed. The Martian core cooled. The magnetic field weakened. The solar wind, which had been deflected before, began stripping the atmosphere away. Over hundreds of millions of years, the atmosphere thinned. The liquid water froze or escaped into space. The planet dried. The warmth faded. Mars became what it is now. A cold, irradiated desert where nothing complex can survive on the surface. But the question that haunts every Mars mission is whether anything survived underneath. Not in any way we would recognize from science fiction. Not intelligent life. Not even multicellular life. The question is much simpler. Did chemistry, in the window when Mars was warm and wet, organize itself into the structures that replicate and metabolize? Did life begin there, just as it began on Earth? And if it did, could any trace of that beginning survive? Sedimentary rock layers that preserve the shapes of ancient organisms. Organic molecules locked into ice for billions of years. Possibly in the deepest subsurface aquifers where liquid water may still exist today. Dormant microbial life that has not been awake since Mars was warm. We do not know, That is an honest answer. We have not found evidence of past Martian life. We have not ruled it out. But if we found it, the implications would be staggering, not just for the history of Mars. For the history of the universe, it would mean that life arose independently on two adjacent planets in the same solar system, from the same raw materials, in roughly the same period. It would mean that the conditions for life, when they exist, produce life. Not occasionally, reliably. It would mean that a universe containing billions of galaxies, each containing hundreds of billions of stars, many of them with planets orbiting in conditions similar to early Mars and early Earth, is almost certainly full of life. The single most important question in the history of science, are we alone, answered by a fossil in a Martian rock layer, or by a microscopic organism still metabolizing in a subsurface aquifer 300 million kilometers from home? The case for Mars is not one argument. It is several layered on top of each other. The engineering case is real. The scientific case is real. And the civilizational case, built on 3.8 billion years of a single world's fragile, interrupted, resilient history, may be the most important of all. 66 million years ago, the sky changed and 75% of species disappeared. We're in the first moments of a civilization with the ability to prevent that from being the end of the story. The Mars colony is not an adventure, it is the backup drive. It is the copy we make before the original is lost. And we have not yet made it. But that backup drive is not an abstraction. It is people. Specific people. People who trained for years, crossed hundreds of millions of miles of empty space, and then stayed. Let's come back to them now. Not to the engineering, not to the civilizational argument, not to the deep time geology of extinction. To one person, growing older on another planet. The first colonists arrive in their 40s or 50s. That is not an accident. It takes years of training, years of preparation, and the accumulated knowledge of someone who has spent a significant portion of an adult life becoming the kind of person Mars needs. They arrive already past the midpoint of their working lives. And then they begin. They spend the next 20 or 30 years doing what they came to do. Expanding the habitat, running the greenhouse, teaching what they know, solving problems that were not anticipated and cannot be escalated to Earth in any useful time frame. The work does not diminish, if anything it deepens, but the body changes. Partial gravity slows bone loss compared to a space station, but it does not stop it. Radiation accumulates. The cardiovascular system adapts to conditions that would alarm a physician on Earth. Aging on Mars is not simply aging. It is aging in a body that has spent decades under conditions no human body evolved to handle. The first colonists reached the end of their lives on Mars, probably in their 70s or 80s, some possibly earlier. And then comes something no mission planner's document fully prepares for. A funeral, not a private moment, not a small gathering, a community-wide event, held in the largest pressurized space available, because that is the only space large enough to hold everyone who knew that person, everyone whose life that person helped build. In a colony of a few dozen people in the early years, the death of one member is not a distant event. It moves through the whole group. The burial is unlike anything on Earth. Traditional burial is not possible. Permafrost makes deep digging impractical. The body is placed in a designated area on the surface, covered with rocks, each one carried by hand. A simple monument, marked with whatever materials the colony can spare. The first Martian cemetery. Future colonists will treat it as a pilgrimage site. They will walk out to it in their suits, stand in the thin, cold air, and look at the stones. They will be standing at the beginning of something. The oldest human graves on another world. Something else was happening. Because the cemetery is not just a place of mourning. It is the first evidence, physical and undeniable, that humans belong to Mars, that Mars has received them, that the relationship is now permanent. Think about the families left on Earth. A daughter or a son, perhaps a teenager when their parent departed, Now 30 years old, 40 years old, making the 6 to 9 month journey across the solar system, hoping to arrive before it is too late. Sometimes succeeding, sometimes not. These are stories that have never existed in human history before. A child who grew up on Earth with a parent on another planet, communicating by recorded message across a 40-minute delay, knowing that the embrace they're traveling toward may not be there when they arrive. Such stories become foundational, not tragic, foundational. They are told and retold in the Martian colony and eventually in Martian literature, Martian song, Martian tradition. A culture defines itself by the stories it keeps, and Martian culture from its earliest years is defined by intentional choice. No one is on Mars by accident. No one was born into it without their parent having chosen it. Every person on Mars in the early generations is there because someone decided to come. That intentionality shapes everything. Language drifts over generations, as it always does in isolated communities, accelerated by the communication delay that makes real-time contact with Earth structurally impossible. New words appear for things that have no Earth equivalent. New holidays emerge around events that mean nothing to Earth, but everything to Mars. The day the first crop survived a full growing cycle. The day the second habitat module was pressurized. The day the first child was born on the surface, and the first colonists themselves begin to change in cultural memory. Not immediately, but over generations, the real human beings, with their specific frustrations and disagreements and failures and late-night doubts, begin to smooth into something larger. Their flaws are not forgotten so much as reabsorbed. What remains is the act. They came. They stayed. They built this. Earth has done this before. Every pioneering generation gets mythologized by the ones that follow. The actual complexity of the people is preserved in documents and letters, if the culture is lucky. What lives in the common memory is simpler, braver, more certain than they ever actually were. The first Mars colonists become the founding myth of a new branch of humanity. Think about what that means across deep time. There are a handful of moments in human history that genuinely divided what came before from what came after. The Wright brothers flew at Kitty Hawk in December 1903. Before that moment, human beings had never left the ground under powered flight. After that moment, the sky was open. Neil Armstrong and Buzz Aldrin stepped onto the lunar surface in July 1969. Before that moment, every human who had ever lived had lived and died on Earth or in its immediate orbit. After that moment, we had touched another world. The first Mars colonists represent a pivot of the same order. Before them, humanity was a single planet species. After them, it is not. For 3.8 billion years, all life that has ever existed on Earth existed only on Earth. Every creature that crawled, swam, flew, or walked. Every organism that lived and reproduced and died. All of it, for the entire history of life on this planet, on this one world. The first Mars colonists end that, not as a metaphor, as a literal fact. Humanity becomes a multi-planet species, and the precise people who make that happen are the ones who do not come back. The first footprints on Mars cannot be erased. There is no wind strong enough, not on Mars with its atmosphere less than 1% as dense as Earth's. No water to wash them away, no vegetation to grow over them, no geological process fast enough to reclaim them on any timescale that matters to human history. The first footprints pressed into Martian dust will remain there for millions of years, long after the people who made them are gone, long after the civilization that sent them has changed in ways we cannot predict, and the atoms that made up the first colonists' bodies do not return to Earth. They become part of Mars, permanently. In the soil, in the rock, cycling through whatever biological processes the colony sustains over generations. They are the first humans whose remains never return to Earth. Not travelers, not explorers who came and left. The first humans who belonged to another world. And now, the closing turn. Throughout everything covered in this script, The frame around the first colonists has been cost, the sacrifice, the things they give up, the return they never make. That framing was accurate as far as it went, but it was incomplete. Not coming back is not the price they pay. Not coming back is the achievement itself. The act of staying is what makes humanity multiplanetary. A crew that visits and returns leaves Mars as it found it, more or less. A crew that stays, that ages, that dies, that buries its dead and watches children grow up who have never known any other sky. That crew is the colony. Their presence is not the means to an end. Their presence is the end. Their deaths on Mars are not losses to the mission. They are the literal foundation of every future Martian's existence. The cemetery is not evidence of failure. It is the most permanent thing the mission leaves behind. The first colonists knew this, not as a consolation, as the whole point. They are the reason the story continues.